Hi everyone, today I will introduce some commonly used conv. Let's start with the most commonly used convolutional layer structure. First of all, we input a 3D tensor feature map, h times w times ci. H and w are the height and width. Ci is the number of channels of the input. It also has an output feature map, ho, wo, co. HO and WO are the output height and width. CO is the number of channels of feature map. For the conv layer, there is a very important parameter, that is the size of the kernel, k times k. Let us take a look at the PyTorch Conf API. There are several parameters, such as the in and out channels, kernel size, stride, padding, bias. In channel is the number of input channels, out channel is the number of output channels. Kernel size is the size of the kernel. It can accept two values or one value. If your input one value, then the kernel will be square. But if you want to have a rectangle kernel, like 3 times 4, it's also fine. Stride is the step size of the kernel. Default is 1. It means it does conv every 1 pixel. If you want to do conv every 2 pixels, you can set stride equals to 2. Why do we want to use 2? It could be used for downsampling. If we have 10 pixels in width, if stride equals to 2, roughly it will do conv for 5 times. The output will be around 5 for width. Padding decides if you want to pad 0 around the border. Bias equals to true, and usually we set it to true. It is the y equals to wx plus b. In total, there are ci times k times k times co plus bias parameters. I set the dilation in groups to gray because common conv doesn't use these two parameters. And they will be used in other convs, which I will mention soon in the following slides. So how do we calculate the output size? Apparently, it is related to the original h and w, so it equals to h plus 2 times padding. Why 2? Because we need to pad on both sides, one to the left and one to the right. And for height, it will be pad one to the top and one to the bottom. So it is always 2 times padding. And then we minus k. Apparently, when the kernel size gets larger, the time to do conv gets smaller. If k equals to h, then we only need to do one time of conv. When k increases by 1, the number of conv decreases by 1. Then we also need to plus 1. Imagine k equals to 1, then we need to get h equals to ho. That is why we need ho minus k, then plus 1. Then we divide the value by stride. Usually, the kernel size and the padding are matched. When kernel equals to 3, padding is usually 1. Why is it? Because when k equals to 3, 2 times padding plus 1 equals to 3. And then minus k, it will be 0. Then ho equals to h divided by stride. Then ho is only decided by h and stride. And if k equals to 1, then padding equals to 0. And if k equals to 5, we usually set padding to 2, because 2 times 2 plus 1 minus 5 equals to 0. So padding and kernel size are usually matching to each other. After the regular conv type, let me introduce a very important conv, that is pointwise convolution. We usually call it 1 times 1 conv because the kernel size is 1. It has several features. First of all, the kernel size equals to 1. Secondly, the number of parameters is ci times co plus bias. Number of parameters are very small. And thirdly, there is no spatial information. Because the kernel size is 1 times 1, which is a single point, it doesn't conv a window of pixels, so it doesn't extract spatial information. Fourthly, it is fully connected on channel dimension. We can see better with the right image. Each blue slice is h times w, and there are ci slices in total. Similarly, there are co slices of ho times wo. So 1 times 1 conv is actually a fully connected layer throughout the channels. The red feature map is connected with all input feature maps. Each red line represents a weight. Similarly, each green line, each purple line represents a weight. So in total, there are ci times co weights. So that is the number of the parameters, ci times co, and then add bias. And there is no spatial communication because each kernel size equals to 1. It gets information of all channels. Usually, it won't be used independently. There are two cases to use it. First is to reduce the number of dimensions. For example, CI is very large, like 2048, and this feature map is too large. I want to reduce the size of it, then I can reduce it to CO, like 1024 or 512. Secondly, it will be used with another kind of conf. I will introduce this conf soon. Next, it is group conf. We separate the feature map to groups. The input is ci times w times h. We separate the feature map to two groups. Then we have hwci divided by 2 and hwci divided by 2, like cutting a cake. Then it will have their own kernels. Then output will be co divided by 2 times ho times wo. In the Torch API, you only need to change one parameter, that is, groups. In default, groups equals to 1. If you change it to 2, then it will cut the feature map to two groups. The number of parameters will be 2 times ci divided by 2 times k times co divided by 2 plus bias. For the first group, it has ci divided by 2 times k times co divided by 2 parameters. Because there are two groups in total, we multiply by 2. Then add the number of bias. So the number of parameters is half size of that of a normal conv. This is used when you don't have enough GPU memory or for compressing the parameters. But it also has one flaw, that is, the information is not fully communicated. Feature map of two groups don't communicate, so we will lose some information. Next is channel-wise or depth-wise conv. This is an extreme case of group convolution. The group number equals to the number of input channels. If we have 6 channels, we will have 6 groups. If we have CI channels, then we will have CI groups. Then we have H times W times 1 in one group. And in total, there are CI of this. Each of them has their own kernel. For the kernel, the input channel is 1, and the output channel is also 1. So each group, there are k times k parameters. In total, there are ci times k parameters. The number of parameters is very small, but it has one drawback, that there is no communication among channels, and the output channel number equals to the input channel number. The good thing about channel-wise conf is that number of parameters is really small, so usually there will be a 1 times 1 kernel followed by depthwise conf, so that the channels could communicate the information. That is, I use a depthwise conf to get spatial information, and then followed by a pointwise conf to get information among channels. Both of these confs have very small number of parameters, and it is very similar to a normal conf layer. So, as I have mentioned before, 1 times 1 kernel is usually combined with depthwise kernel. It is widely used when we have limited GPU memory. There is also dilated conf. In picture A, it is a normal conf, a 3 times 3 kernel. The receptive field is also 3 times 3. But in some cases, we want to make the receptive field larger, but 5 times 5 or 7 times 7 kernel size will lead to much larger parameter size. One way to solve it is to use dilated conf. The number of parameters doesn't change, but the receptive field increases. And we can also use different dilation size to get different level of information. It is widely used in image segmentation because it needs to see wide, and the output feature map size will be like this. The common way to calculate the output size, but need to minus dilation size as well. Dilation conf is also given by PyTorch. You can simply set the dilation to 2 or 4. The last conf I will introduce is transpose conf. It is the reversed operation of normal conf. It can be used for upsampling. A normal conf, after doing the ops, the feature map becomes smaller, but for transpose conf, it gets larger. It's provided by Torch API. The parameters of it is the same as the normal conf. That's all. Thank you.